In this equation, we can see that y cannot easily be written as the subject of the formula. And so because I want to find the derivative of the equation, I'm going to use implicit differentiation. If I go according to the method that I showed you before, it means that I still want to find the derivative of the left-hand side. There are two terms on the left-hand side, so I want to find the derivative of the first term and add that to the derivative of the second term. I also want to find the derivative of the right-hand side of the equation, so I must find the derivative of the constant 4. Two of these terms are easy to do. The first term on the left-hand side has an expression in the variable of x, and that is the variable that I need to use to find the derivative. In other words, using the power rule, I get that the derivative of x squared is going to be 2x. Going to the right-hand side, the derivative of a constant is always 0. My problematic term was the second term on the left-hand side, and if I use the chain rule, I can say take the derivative of the expression that I've been given in the variable of y and times that by dy dx. So now for the second term on the left-hand side, the derivative of y squared in the variable y is going to be 2y, and I must still times that by dy dx. You can see now by changing the subject of the formula, I can get that dy by dx is going to be equal to minus 2x all divided by the factor 2y. If now I want to know the exact slope of the tangent to my line or to my equation, then I need to find the gradient of my tangent. Now you can see that I've used both the x and the y coordinate to find the derivative, so it means that I must substitute both the x and the y coordinate of my point of contact. In other words, the derivative of the tangent at this particular point, when x is the root of 3 and y is 1, is going to be minus 2 times by the root of 3 all over 2 times by 1. So the gradient of the tangent to my equation is going to be minus the root of 3.